Okay, good evening, everyone, and thank you for joining us tonight on our climate change late night event. So this is our first late night event of the 2022 year. So we're excited to be back and doing these again. I'm Lauren Adamo, the director of the Geology Museum. We have Ria Sarkar, who's one of our tour guides at the Geology Museum, and I've got my co-host here, who hopefully will be quiet. Or at least happy during our first part of our evening. So we're going to start off with trivia, and then we will go to a craft. And then finally, we will end the evening with our guest speaker, Melissa Lau, who is a former PolarTREC teacher who's going to talk to us about her work in Alaska studying plants and how that how they interpret the results for climate change. Okay, so we're going to get started. So for those of you who are just joining us, who haven't done this before, you can use your phone to scan this QR code, or you can go to menti.com and enter the 8-digit code that you see on the screen, and that will have the questions that we will be sharing, and you can put your answer in there so we can see live what the score or what our audience is picking for these answers. Okay, so let's get started. Oh, I keep pushing the wrong button. Okay, so question number 1. During which geologic period was Earth warmer than it is today? So A, the Hadean, about 4 billion years ago, the Cretaceous for B, which is 145 to 66 million years ago, C, the Eocene, about 66 to 23 million years ago, or D, all of the above. Ria will be tracking our scores and let us know what people are selecting.
So I see a lot of answers coming in right now, so I'll wait a few more seconds. And it looks like it's a tie. Oh, no, it's not a tie anymore. Okay, so it looks like most of you have chosen the option D or all of the above.
Okay, let's see. And that is correct. So the answer is D, all of the above. So while the Earth has been warmer in the past than it is today, they're significantly warmer. The issue with climate change today is the rate at which the Earth is warming. So because it's happening so fast, plants and animals and us cannot adapt as quickly as the climate change is occurring now. Okay, question 2. What percentage of climate scientists agree that human activity is the primary cause of today's climate warming? Is it A, 97%, B, 74%, C, 56%, or D, 35%? Clay's telling us his answers, so.
So it looks like everybody has chosen option for A, 97%.
All right, so let's see what we have. And that's correct, A, 97%. So almost all climate scientists agree with the overwhelming evidence that humans are the cause of climate change. Okay, question 3. What is the greenhouse effect? Is it A, a law about climate change? B, when gases trap heat in our atmosphere? C, when you build a greenhouse? Or D, when gases escape Earth's atmosphere into space?
So it looks like we're getting a lot of answers in for both A and B, but it looks like majority have chosen B, when gases trap heat in our atmosphere.
All right, let's see what the answer, and that is correct, B. So the Earth receives solar radiation from the sun, some of which is absorbed by the sun, the rest is reflected back to space. But the gases in our atmosphere trap that heat, making our atmosphere warmer. Excuse me. Okay, so which one of these is not a greenhouse gas? So A, water vapor, B, methane, C, oxygen, or D, carbon dioxide. So which one of these gases does not help trap heat in our in the Earth's atmosphere?
Okay, so it looks like we're getting a lot of There's a tie now between A, water vapor, and C for oxygen.
All right. So answer is C, oxygen. So you can see in this picture here, a list of the different types of greenhouse gases. Although oxygen does play a significant role in our atmosphere, is not responsible for trapping heat in the atmosphere. Okay, question number 5. Which greenhouse gas is the most effective at trapping heat in the atmosphere? Is it A, water vapor, B, methane, C, ozone, or D, carbon dioxide?
Oh, it looks like we're getting a lot of answers for D, carbon dioxide.
Carbon dioxide, okay. Let's see what the most effective. And it's actually A. So that was a tricky one that not a lot of people got correct, which is okay. We're learning together. So A, water vapor. So most people think carbon dioxide because it's the one that we talk about the most of, increasing the effects of global warming. But water vapor is actually much more effective at trapping the heat. So it estimates that between 36 and 70% of greenhouse effect is due to the water vapor in the atmosphere. Okay, so if you just joined us, we're playing trivia. And if you'd like to play along with us and answer on the computer, you can scan the QR code with your phone. It'll take you to menti.com, or you can type menti.com on your computer. Someone's very happy. This is better than screaming. So, and type the 8-digit code that you see to play along with us. Otherwise, write your answers down, and please feel free to put your answers in the chat, and let us know how you're doing so far. Okay, so question number 6. What would happen if we removed all of the greenhouse gases from the atmosphere? A, the earth would cool a little. B, the earth would get really cold. C, the earth would get warmer. Or D, nothing, everything would stay the same.
So we have a majority of people answering for option B, which is the earth would get really cold.
Okay, let's see what everyone says. So yes, the answer is B. It would get very, very cold. So without the greenhouse effect, Earth's average temperature would drop from its current temperature of about 57 degrees Fahrenheit to as low as 0 degrees Fahrenheit. So yes, that would be a very different world than what we live in today. Okay, question number 7. How do scientists collect data about climate change? So A, using remote sensing satellites. B, ground-based measurements of temperature. C, using proxy data from tree rings and ice cores. Or D, all of the above.
It looks like we're getting a lot of answers for option D, all of the above.
All right, let's see. The correct answer is you're correct, is D, all of the above. So in order to study climate change, scientists use a whole bunch of different methods to measure how the temperature is changing currently and how things are changing in the past. And we've had a lot of these scientists present in our Ask a Geologist series and at some of these late night events as well. And that's actually what Melissa Lau is going to talk about. She's going to talk about some ground-based measurements in plants and how that tells us that the climate is changing. And what Ria and I we work on sediment cores in the past, and we look at the proxies and sediment cores to see how temperature has changed in the past. So lots of really cool stuff. Okay, so question 8. What is the name of the international treaty or agreement about climate change? Is it A, the Climate Change Agreement, B, the London Agreement, C, the Paris Agreement, or D, the Greenhouse Gas Agreement?
So it looks like a lot of people are putting down option D for the Greenhouse Gas Agreement.
Okay, and I see Danny and Josh answering in the chat. Thank you for playing along with us. I think they put C, Paris Agreement. So let's see what the correct answer is. Oops, I'm sorry. And it is C, the Paris Agreement. So this is an international treaty on climate change that aims to keep the increase on average global temperatures below 2 degrees Celsius. So this is what scientists believe is kind of the threshold. We can keep it under 2 degrees C, that will avoid a lot of the catastrophic events of climate change. Okay. Question 9. Which country emits the most carbon dioxide? Is it A, China, B, the US, C, the United Kingdom, or D, Russia?
So far, we have a tie for all of the options, but let's wait for a few more people to cast their votes. And it's actually now a tie between A, China, and B, the USA.
Okay, let's see. And the answer is A, China. So US is a second, but China is about more than double than what the US emits. So China is the number one, around 28% of the global emissions, and US about 15%. Okay, which of these is a consequence of climate change? A, animal extinctions, B, extreme weather events, C, rising seas, or D, all of the above?
Okay, so it looks like we have a lot of answers coming in for option D, which is all of the above.
Okay, and yes, they are correct. The answer is D, all of the above. So those are just some of the consequences. Some of the other ones are increased ocean temperatures, melting glaciers, coastal flooding, and a whole list of other things as well, unfortunately. Okay, so again, if you're just joining us, we're about halfway through our climate change trivia. So you can scan the QR code or go to menti.com and enter that 8-digit code, and that will pull up the questions that we are answering live, and how Ria can read your answers. So please join us and let us know, since we're halfway through, put in the chat what your score is. Okay, question 11. What happens to precipitation, so rainfall and snowfall, as average global temperatures increase? So A, precipitation increases, B, precipitation decreases, C, it stays the same, or D, scientists do not know?
So far we have equal answers, so a 3-way tie. For A, precipitation increases, C, precipitation stays the same, and D, scientists do not know.
All right. So the correct answer is A, precipitation increases. So if it's warmer, there's a more active water cycle. So it means that there's more evaporation and more precipitation. So this also includes more extreme weather events, things like hurricanes and cyclones and all that not so fun stuff. Okay. Question number 12. How much has the global average sea level increased in the last 100 years? So this is an average for the entire world, not just in specific locations. So it's A, 2 inches, B, 7 inches, C, 1 foot, or D, 2 feet?
So it looks like we have a three-way tie again, but I'll wait and see if there's any tiebreaker here. And we eliminated one, but it's still a tie. So we're down to B, 7 inches, and C, 1 foot.
Okay, let's see. So the correct answer is B, 7 inches. So on average, global sea level has risen about 7 inches, with predictions of it increasing another 1.5 to 3 feet by the year 2100. So that would be a lot. You can see the picture. This is downtown New York City, showing a computer simulation of what that 1.5 to 3 feet increase in sea level would mean for lower Manhattan. So it doesn't seem like a lot, but it is actually a lot of land that would be underwater. Okay, question number 13. How much have global average temperatures increased in the last 100 years? So A, 0.6 degrees Fahrenheit, B, 1.4 degrees Fahrenheit, C, 2 degrees Fahrenheit, or D, 4.1 degrees Fahrenheit.
So it's a steady tie so far between C and D. But I'll wait one more second and see if there's a tiebreaker. And nope, we're still at a tie. So C for 2 degrees and D for 4.1 degrees.
All right, let's see. So the answer is actually B. I don't think, was it the C and D were the highest choices?
Yeah, nobody put B.
So on average, the global temperature has already risen about 1.4 degrees Fahrenheit in the last 100 years, and it is projected to raise somewhere between 2 and 12 degrees by the year of 2100. And we'll talk a little bit about these climate anomalies of how abnormally warm it's been in the last like 40 years, which is what this graph is showing. When we get to the graph, you'll get to color these things. So, okay, question 14. So far, the strongest impacts of climate change have been felt where? A, at the poles, B, in the tropics, C, everywhere is feeling the effects the same, or D, we have not felt the impacts of climate change.
So we have a majority of answers coming in for A, at the poles.
Okay, let's see. And that is correct, the poles. So the poles are extremely sensitive to even the smallest temperature change, which causes the ice sheets and glaciers to melt. So that is because of something called positive feedback. So it causes lots of melting, and this is a big problem of extreme melting at the poles today. Okay, question 15. Which of these is responsible for the most CO2 emissions in the United States? A, electricity, for the producing of electricity, B, agriculture, C, transportation, or D, industry.
So we have a tie, and it is between a three-way tie now. So it's between A, electricity, C for transportation, and D for industry.
All right, let's see what the answer. And the answer is C, transportation. So transportation in the US, so cars, trucks, airplanes, all of that, accounts for 29% of the greenhouse gas emissions. And then electricity is a close second of about 25% of the emissions. Okay, I think we are last reminder to join. So again, if you just joined us, go scan the code and it'll take you to menti.com and enter that 8-digit code so that you can play along with us and answer. And hopefully you're tracking your score so you can tell us what your score is at the end of trivia. Okay, the last 5 questions. Question 16, what are some things you can do to help reduce greenhouse gas emissions? A, waste less food. B, eat less meat. C, use renewable energy sources. Or D, all of the above.
So it looks like everyone has put down for D, all of the above.
Yes, I see some people in the chat selecting D as well. And you are correct. So all of those can cause less greenhouse gases to be released into the atmosphere, which decreases the greenhouse effect that is warming our planet. Okay, question 17. Which one of these is a good source of clean renewable energy? A, wind power, B, solar power, C, geothermal power, or D, all of the above?
So it looks like we're getting a lot of answers for D, all of the above.
All right, chat says D as well. So answer, yep, is D. So all of those, including also these other renewable resources that you see listed on this figure, are all really good sources of clean renewable energy and alternatives to fossil fuels. Okay, question 18, almost at the end. How much of the United States' current energy use comes from renewable sources? Is it A, 12%, B, 24%, C, 55%, or D, 78%?
So we have a majority of answers coming in for A, 12%, but B is also a close second choice, so for 24%.
All right, yes, I see answers of A in the chat. So let's see what the answer is. And the right answer is A, 12%. So a very small proportion of our energy comes from renewable energy. So we have a very long way to go to get away from our fossil fuel consumption. Okay, 2 more questions. Which renewable energy source is the fastest growing in the world? Is it A, wind energy, B, solar energy, C, hydropower, or G, geothermal energy?
So it looks like we're getting a tie between A and B. So I'm gonna see if there's any tiebreaker here. Nope, still a tie. So A for wind energy and B for solar energy.
All right, let's see what the answer is. And the answer is B, solar energy. So solar energy is currently the fastest growing renewable energy source, but it only counted for about 2% of the world's electricity in 2018, but this is going up every year. Okay, our last question, if it will load. Oh, and I just gave you the answer. Pretend you didn't see that. It got stuck. What technology can provide society with the quickest, cheapest, carbon-free energy and halt climate change? So A, solar panels, B, clean coal, C, electric cars, or D, none of the above.
Okay, and it looks like a majority of people are putting down option A for solar panels.
Okay, so the answer is D, none of the above. So not there. The solution is that there's not a single technology that's going to solve this energy issue of going to carbon-free energy. So we must use a variety of energy sources in order to get ourselves to a higher percentage of clean renewable energy versus on fossil fuel dependence. Okay, so great. Thank you for playing. So how did you do? Tell us in the chat. So if you got between 0 and 10, you're a weather enthusiast. 11 to 15, you're a meteorologist, and between 16 and 20, correct, you're a climate analyst. Okay, so tell us how you did. I think a lot of people are going to be climate analysts because there were a lot of them had the right answer in this. So yes, thank you for playing climate trivia with us. And Ria, we're going to turn over to you again so that you can walk us through our climate change craft. So just let me know when you want me to advance the slides for you, okay?
Thank you, Lauren. Yeah, so you can go ahead to the next slide. And so we're going to be coloring the climate record. So if you want, you can go ahead and grab your supplies now, although I'm just going to talk just a little bit to give you a little bit of background, and then we'll jump right into the activity. But if you want, in the meantime, if you want to get your supplies, you'll need graph paper. You will need the climate record, and I'll show you where you can get the climate record. You'll need something to color with, so it could be crayons, colored pencils, or markers. And the colors you will need are purple, red, 3 shades of pink, white, light blue, and dark blue. And if you would like, you can get scissors and tape. Those are optional. It's up to you, and I can explain that in just a minute. And I am going to give you a little bit of background, and then I'll go over again what materials you'll need in case you missed that. And I'll show you where to get the climate record as well. Okay, and Lauren, you can go to the next slide. Okay, so before we do that, what is climate change, right? Maybe you've heard of climate before and you've heard of weather, and you're not exactly sure what the difference is between them. So you can think of weather like the daily changes, like it's going to snow tomorrow, so maybe I should wear a hat and I should take my gloves. Or maybe it's going to rain next week and I should take an umbrella. So climate is basically weather on a period of 30 years together. So climate change is a long-term change in the temperature and weather patterns. And these changes can be natural or man-made. And Lauren, you can go to the next slide. And so we know that the climate has changed many times in the past in geologic history. But what we do know is that it's changing a lot faster today, the rate of change, than it ever has before. And this is happening mainly because we are burning so many fossil fuels. And like you saw in the trivia, carbon dioxide is a greenhouse gas that is being released into the atmosphere. And it's kind of like a blanket for the Earth. And it's keeping us warm, but maybe a little too warm. Next slide. And so we're going to be, for our activity, we're talking about an anomaly. And so an anomaly is just something that is different from the normal or the average. And so you can see, so this is a graph from 1920. And so the anomaly here, you can see that it was a lot colder at that time, but it has been getting increasingly warmer. So you can see warmer than the average, right? And so this is kind of what we're working with for our climate record that we're coloring today. Next slide. Okay, so back to what you'll be needing. Again, you'll need graph paper, you'll need the climate record, and there's a little screenshot there, but you can get it off of the museum website. You can scan that QR code as well. It'll take you right to it. And I can also share my screen and show you where to get to the links. And you'll need crayons or colored pencils. So you'll need purple, red, 3 shades of pink, white, light blue, dark blue, and it's up to you if you want to use scissors or tape. Okay, so I am going to share my screen now, and I will show you where you can get some of the supplies. Okay, so I'm on the Rutgers Geology Museum website, and I'm on our climate change late night page here. And so you can see right over here where it says supplies needed, here's graph paper and the climate record. And so here's the graph paper. If you don't have graph paper, we have it here, so you can print this out. And the climate record is right over here. And here's the key, right, the color key. So you can see that the blue colors are a lot cooler. And then the darker reds and purples are hotter than the average. And so here we have on the left side, we have the years since 1922. So this is a record of 100 years. And we're going to be coloring this, and I'll show you how to do that. And it goes all the way up to 2021. Okay, and so I will start I'm going to change my camera view, and I'll leave this up for you in case you need it. And I'll go back actually to this one here. Yeah. Okay, so I actually also created a climate record before to show you all, just so you can see what we're doing. And so here you can see that I cut strips from the graph paper that I had. So I made it about 5 boxes wide, and I cut basically 4 sections. So I'll show you how to do that. But I made this long strip, I taped it together, and then I colored it. And so that's what you all are going to be doing today. It's up to you if you want to make it like this by cutting it. You also don't have to cut it if you don't want to. You can also make it by using 4 sheets of paper. And I can show you an example right over here that Lauren actually had done earlier. So here's another way to do it. So you can see she used 4 pages, 4 graph papers, and she did her climate record like that. The one I'm showing you is a lot thinner and might require a little less coloring. So let's get started. So I have here some paper, and I have already cut 2 strips out, but I'll show you how I can do one. So I'm going to count out 5 boxes here because I want to make my strip 5 boxes wide. Okay, and I'm just going to cut a strip right there. Okay, so you can cut a strip like this, and you can cut 4 strips. You might not need the entire strip. It might be a little long, so you can just trim it at the end when you're finished. So I'm going to tape this on to the other 2 strips that I cut. Okay, so I'm going to start coloring now, and I have my colors here. So I'm going to start with the year 1922, and I can see that from 1922 to 1925, I'm going to be using this light baby blue. So that's going to be, that's for 4 years. So every row here is representing 1 year. So here's 1, 2, 3, 4. And this might take a little longer, so it's okay if you don't finish this right now. So you can continue to do this even after we're done with the activity. So feel free to continue to use this chart and finish up your climate record. And at the end, you can take a picture of it and post it to the Padlet. And I'll show you the code for that in just a minute. But so now I've done 1922 to 1925, and now I can see for 1926, it's white. So I'm going to leave a space. And now I have 2 more years from 1927 to 1928. That will be the light blue color. So I'm going to color that in. And now I have a dark blue color for 1929. Okay, and now for 1930 and 1931, I have, again, two of those years are gonna be white. So next I'm gonna go to 1932 and I see that is that light blue color again for the next 2 years after. So I'm gonna make sure I get that blank year there. And I have my 2 light blue years. So you can see it's pretty cold around this time, right? Cooler than the average. We're not even getting into like the reds or the pinks yet. Okay, so that was 1928 or no, 19, let me see. Yes, okay. And now I'm in 1929. So again, I have this darker color. And then for the next 2 years, again, it's blank, it's white. So I skipped those 2 years I have, and I don't have to color it in white since my paper is already white. Then I have 2 years that are light blue again. And you kind of see how to do this, right? So you can, again, if you don't finish right now, that's okay. You can continue to do this on your own later. And I'm gonna skip the other year. Then I have 2 years that are light blue again. And now I have the next 3 years, which are white. So I'm gonna skip that. And now I have a color change. So I get to use light pink. So you can see now it's starting to get a little warmer than normal. So I'm going to use this light pink color.
Hey, Ria, why don't we spotlight your thing? Because we can't really see your
Okay, you want me to stop sharing?
yeah, just so we can see your. And Julie, would you spotlight that camera for everybody? There we go. Perfect. Thank you.
So I'm skipping those 3 years since they're going to be white. And now I'm in 1940 and it's a light pink color and it's only for 1 year. So I'm only going to color in that one row light pink. Now I have a pink color, which is even warmer. So the temperature anomaly is plus 0.25 through plus 0.42. So I get to use a darker pink color for this for 1941. Now I go back to the light pink for the next 2 years. And then I go back to the darker pink for another year for 1944. So you can see it's starting to get warmer and I don't see any more blue colors after this, not really. Or it's getting less, right? Less frequent that we have that blue color. So the next one I have is another light pink after 1944. And then we have for the next 4 years, it's white. And then we have a light blue in 1950. And then the next 4 years, again, are white. And then I have 2 years of light blue. And again, you can either cut strips like this, or you can just do it on 4 whole sheets of paper. It is completely up to you. You could even use colored beads if you wanted to make like a climate change necklace. You could do that with the same colors. And so I'm not going to finish my whole strip here, but I can show you again the other one that I had made before. And so here you can see we started off with these blue years, right, in the 1920s, and it started to get warmer and warmer and warmer. And then once you get towards the end into, I think it was around the 1980s, right? You start to get increasingly more of those pinks. And then you start getting the red in 1998. So there's the first red. And then we get into the 2000s where it's mainly just the red color. And I'll have to go back to see exactly what the anomaly was for that. And then all the way at the end from 2015 to 2021, it has pretty much been all purple. So if we go back to the numbers for that, red was a temperature anomaly of plus 0.61 through 0.78, and purple was 0.79 through 0.96. So there's a big jump there. Okay, and so I can show you once you're done with your climate record, once you're done coloring that, you can actually go to the Padlet and you can take a picture and post it out there so that we can see what your climate record looks like. So let me go back to that and I can show it to you. And here's the Padlet, and I'll put that QR code up there for you for another minute in case you wanted to, in case you're done with one of yours, but no rush, take your time. And you can show us how you've done with your climate strips and what it looks like. All right. And so I think we're excited. We're looking forward to seeing your climate records and how you all have colored it in. And Lauren, would you like to introduce our speaker?
Sure. Would you like to stop sharing? Oh, I've got my dog barking now too. Yes, this is what I expected. Okay, can you unpin Ria, Julie?
I did, I think.
Okay, I'm going to do a very quick intro because I have a cranky baby now. So I'm very pleased to introduce Melissa Lau. I know, it's exciting. I had the pleasure of being a PolarTREC teacher with Melissa almost 4 years ago now, which is crazy how long ago it was. So I loved hearing about her expedition, and I can't wait for her to tell all of you about all the cool stuff she did in Alaska. So Melissa, it's all over to you.
Thank you, Lauren. And it's so nice to be here. And I appreciate the opportunity to share that experience that I had in 2018. That was the year that I went. I'm going to go ahead and share my screen. And I'm going to jump right in. A lot of some of the things that are on my presentation are going to be just reiterating a little bit about what you've already talked about with the trivia and with the climate record, but I think it bears repeating. It's such a important topic. I am from Piedmont, Oklahoma, which is northwest of Oklahoma City, so right in the center of the state. And I am a high school chemistry teacher, but in a past life, I was also a middle school science teacher as well. This is actually my first year teaching high school. And I have learned that high schoolers are basically just, I don't know, they're middle schoolers in a bigger body. They're fantastic though. And I have love my job and the work that I do. And it offers me opportunities to work with organizations like PolarTREC. And so I'm going to just jump right in. So just a real quick recap, what climate change is. Again, that weather, climate versus weather, the weather is the daily changes that we notice, that we feel, that we pay attention to, because we have to decide, are we going to be able to play outside? Do I need a coat or rain boots? Is it going to be windy today? That sort of thing. And then climate is the normal weather of the place. And the term normal in this case isn't, it's more of a mathematical term. It's another word for average. So climate can be different for different seasons. So you could have a hot and dry climate where you live in the summer, like we do here in Oklahoma. You could have cool and rainy winters, and different places will have different climates. You could also live, you might live where it snows all the time, or you could live where you can, swim outside in February, which is not the weather that we're experiencing right now. It's snowing here now. With Earth's climate, though, it gets even bigger. So we can even think of climate as being local, but then we can broaden and zoom out even further and talk about Earth's climate. And there's three major factors when we consider Earth's climate. We look at, average temperature of our planet, the average precipitation of our planet, and the average surface speed, wind speed of our planet. And so our average temperature is 58 degrees Fahrenheit, 14 degrees Celsius. And so that's what happens, that's the temperature of our planet when we take all of the temperature points, data points across the globe, and then average them out. So we have very, very cold temperatures at our poles. We can have very hot temperatures towards the equator, and then more temperate in between. But when we average them all out, the average temperature of our planet is about 58 degrees. Our planet average precipitation is 39 inches a year, or about roughly 100 centimeters. Again, that's taking all of the amount of precipitation data that is collected across the globe and then just averaging those amounts out throughout the year. And that would give us our yearly precipitation. So some places get a lot less than 39 inches. Some places get a lot more than 39 inches. But average precipitation for our planet is 39 inches. And then the wind speed averages out to 7.4 miles per hour. And again, other places like where I live, it can be very, very windy. And then there are other places that really don't experience a lot of wind. Climate change is a change. When we see the term climate change, that's referring to a change in the usual weather, the usual climate found in a place. And it could be a change in how much snow a place usually gets in a year. It could be its usual temperature for a month or a season. It could be like a phenomenon that we're experiencing is the extending of a storm season. In Oklahoma, we typically have tornadoes in the spring, and we are prepared for that. And we have a secondary storm season in the fall. And it's the secondary season that has caught the attention of the people that live around here, because now we're suddenly getting tornadoes in the fall more often. And that fall storm season is extending longer because it's warmer longer. So it's not unusual to have in our recent climate history is, to have tornadoes in October and November, where when I was a child growing up, many, many moons ago, it was not nearly as common. It was so rare that you would even get a thunderstorm, much less a severe storm. So extending storm seasons is something else that we're starting to notice. So climate change is also a change, so that's more of a localized example, but climate change is also, again, talking about that global climate. It's a reference to the change in the Earth's average temperature. And that's typically what we think of whenever we think of climate change. We think of a warming of our planet, but it's also, because of that warming, that's also changing where precipitation would normally fall on Earth. Places that are getting drier, other places are getting wetter. And so those changes are often tied to that changing temperature. And weather can change in just a few hours or days, but as it was said earlier, climate is an aggregate or an average of many decades of weather data, and climate can take hundreds or even millions of years to change. And our planet has always had a changing climate, and it was mentioned in the trivia game that there have been times in the past where the Earth's climate has been warmer than it is now, so roughly 65 million years ago, that we didn't have polar ice caps. Our planet was much warmer. And then there's been times when it's been a lot cooler, like in this picture with the woolly mammoths. We think of the fun movie Ice Age and all of the sequels, that this would have been happening, around 40,000 years ago. It was a lot cooler. And so our planet has these natural warming and cooling cycles. And these times typically last thousands or millions of years. And that is the big difference. Why is it such a big deal if it's always been happening? It's the rate of change. These changes are now happening within decades or a few hundred years instead of just thousands or millions of years. So people who study Earth's climate can see that Earth's climate is getting warmer, and the Earth's temperature has gone up about 1 degree Fahrenheit in the last 100 years. And it doesn't seem like a lot, but when we're talking about, that average temperature and how many data points it takes to raise an average, I always tell my students that think of the increase of the Earth's global average temperature going up. Think about like you failed a test, and how many good grades does it take to be able to pull that average back up if you totally bomb a test? That's kind of what we're looking at here, is Earth's temperature going up about 1 degree. Think about how much the individual data points have to increase to be able to pull that average globally up. It takes a lot of changes, but these small changes in Earth's temperature has big effects, and especially when those changes, like I said, were happening in a short period of time. Environments don't have an opportunity to adapt and be better suited for a new climate. This is a picture of Bear Glacier, which is found in the Kenai Fjords National Park in Alaska. And the picture that's on the left is from 2012, and the picture that is on the right is from 2019. So just 7 years later, just under 7 years later. Some effects are already happening. The warming of Earth's climate has caused some snow and ice to melt that would normally stay frozen year round. Warming has also caused our oceans to rise. So as these glaciers are melting, it's introducing land ice into our ocean systems, and that's what's causing the sea level rise. It's also changed the timing when certain plants grow, which brings me to my work with Florida International University. This was the group that I was paired up with and teamed with PolarTREC. And so the team, it was a very small team, small research team. This was the bulk of us. So on the three of us, the picture that's on the left, Dr. Jeremy May is, I don't know if you can see my pointer or not, but he is on the far left. I'm in the blue in the middle. It was raining that day, or had just been raining that day. And the young man with the baseball cap, well, they're both wearing caps, I guess. The younger guy on the right in that picture of three, that's Matthew Simon, who was our our postgraduate. He was working on his master's, and he was in the field with us that year. And then the lone guys crouching in the snow, taking a picture of people taking pictures. That's Dr. Steve Oberbauer, who is the principal investigator. He is the lead of this research project. Dr. May is the postdoc that works on the program and coordinates a lot of the field work in the summer. So the team at Florida International University, they study, here's their really fancy title, Phenology and Vegetation Change in the Warming Arctic. And I really had to practice really, really hard to be able to say that title consistently. It sounds very very impressive, which it is, and it's very important work, but big words can often, give you the impression that you can't understand something. So if we look at the term phenology, that may not be a term you're familiar with. You probably recognize the suffix of ology, which is the study of, but then pheno is literally, it means shining or appearing or seeming. And so phenology is the study of the timing of changes in nature. So when do, what types of changes do we see in plants and animals in our environment that happen at different points in the year? So if we do a little phenology practice, and you can put your answers here in the chat. So if I showed you this picture, what could you tell me about the time of year that this picture was taken, this photograph was taken? What would you say when this picture was taken based on your observations? I am going to pull up the chat and just see. So I see Danny and Josh put fall. Yeah, so we can probably get some clues. Oh, and then Ria, mom says fall. So this picture would have been taken in the fall, and we can get those clues from lots of things. We can look at the trees and see the brown leaves. We can see that some of the trees are bare. We can see, if you know anything about the timing of when deer have their young. And you might know that if you see a spotted coat on a deer, that's a baby, that's a young deer. And so that might give you a hint that this picture was taken in the fall when this baby was probably, looks a little older, but still young enough to have its fawn coat. So yes, and that's basically what phenology is. We use phenology all the time to identify changes in the season. Winter's coming, or fall is coming, or spring is near, because we can feel these changes. We can see the changes in the plants and in our environment around us. And that gives us clues as to what we can look forward to in those changes. So how did we study this? How did we study these changes? So we did qualitative observations, which is just a fancy science way of saying we looked at stuff and then wrote down what we saw. So this particular program with Florida International. This is an LTER, which is a long-term ecological research project. They've been collecting data since the 1990s, which to me doesn't sound like that long ago, but for some people, when they start referring it to the late 1900s, it hurts my heart a little bit. But so they have been collecting data for several decades in the same area, several areas in Alaska. And that's a picture of me, again, with my blue raincoat, taking qualitative observations in the field. And I'm standing on these railroad ties that mark off what's called phenology plots. And these phenology plots have been staked out for several decades, and they've been watching them change over these decades. And we kept track of, we would go out twice a week, and we would record when we would see the leaves budding, when we would see bud breaks, when the leaves were starting to break out of the buds, greening up, when we would see flowers budding and then flowering. They also kept track of when fruits would appear on the different plants, and just the overall greening of these plots. And of course, we would track the time and the date, which you can see in the right picture. That is one of our field field records that we would take out with us, because when you're in the field, we're not anywhere close to where technology would be reliable. It's fairly isolated, and you didn't want to take your devices out into the rain and into the weather, into the elements. And so a lot of the work was still done, old school paper pencil. And then we would come back and then input that data into a digital database. We did use some fancy equipment. So the picture on the left is Dr. May setting up what's called the MISP, the MISP, which is the Mobile Instrument Sensor platform. And this is really kind of the key thing with Florida International and the work that they do in the tundra in Alaska is with this MISP. It runs on this transect, runs on these cables across a strip of ground. We would run it every day, except for Sundays. And on this platform, they could put in different types of sensors that could collect all kinds of different data that are more quantitative. And so you see that the term has changed a little bit. That just means instead of just using my eyes and making a judgment about how green something is, we have technology that can take actual measurements and have a quantity to how green something is. And they could track all kinds of different things. The idea for this, though, is unique to Florida International. Dr. Oberbauer was thinking that, we have people on the ground that are making these qualitative and quantitative observations about changes that are happening. And then we have satellites in space that are looking at the same places, but there's not really anything that's in between. So you had, boots on the ground, you're looking, at a 10 centimeter square of plants and making your observations. And then you would have a satellite, that's a mile above and looking at a kilometer square of tundra and making observations and collecting data. And the idea behind the MISP was to be this bridge between the measurements that could be taken by hand and on the ground and the measurements that are taken in satellites in space. And it was the scaling up of this data that helped to, it was like ground truth being the what we were seeing on the ground, what we were seeing in space. We had this intermediary in between instrument that was helping us see that, confirming that what we were seeing on the ground, confirming the measurements in space, and helping to keep those measurements and see the accuracy of that. Then we were also using, I love that picture. That is the beautiful mountains in Alaska there, makes me miss them. The little short plastic things are called OTCs. This is something else that Florida International uses. They're called, they're open top chambers. And think of them like little miniature greenhouses. And so this is an experiment that's been running for several decades, several years for sure. And they have plots that they put these OTCs, these open top chambers, to help simulate a warmer tundra. And then they can compare how the plants are changing in the OTCs versus just the regular tundra plots, the control plots that were nearby, to see how much the temperature warming by 1 or 2 degrees, how much of a difference that would make to the plants as far as when they were getting green, or when they would put on fruit or flowers, or when they would go into what's called senescence, when they change their colors in the fall and get ready to overwinter. We also used the green seeker. This is something that's used by some farmers. They can use it to determine if they need to fertilize a crop. If their crop is green, then they know that it's healthy and it's doing well. If it's not a certain greenness, then they can add some fertilizer to make it healthier. And that's the idea behind green seeker, because my idea of what green is may not be the same idea as somebody else's green. So this actually puts a number to the greenness of a plant. We can measure how green a plant is using a instrument like the green seeker. And then there's a picture of me on the right, where I am taking permafrost depths. That was another environmental factor that we were tracking. And so you just simply put that metal stake into the ground and until it hit permafrost. And permafrost is this permanently frozen soil. It never ever thaws. So it's like hitting a rock, a layer of rock underneath. So we would go out every time we went to the phenology plots, we would track the permafrost melt as well in several places in the plot. You would put the probe into the ground, and then you would measure just simply with a ruler how many centimeters deep did that probe go into the ground before it hit permafrost. So the other part of that title of the phenology and vegetation change in the warming Arctic, vegetation change is slightly different. So phenology is the timing of when the plants were doing their greening up, when they were, I'm going to speed up a little bit, when they would green up, when they would go into senescence or change colors in the fall. But vegetation change is the change of species dominance. What types of plants are more dominant or less dominant in the Arctic? And so this is a picture of a birch tree. And you might have birch trees where you live, but they probably don't look like this. They are very small in the Arctic. This is Betula nana, which is the botanical name for this particular species of birch. And it's about the size of a bush, you know, maybe knee to waist high. But as the Arctic is warming, some of the shifts, the dominance has changed. With the warming Arctic, the permafrost is melting, which means plant roots can go deeper before they hit the frozen ground. And deeper roots means that the plants can grow taller. And there's also a longer growing season. It's getting warmer earlier and staying warmer later, so the plants can grow more during their growing season. So we have this vegetation change in this plant. Sorry, I got distracted by the chat. So yeah, these shrubs are just getting taller and taller and taller, which means they're providing more shade. And that led them to the shade plots, which is on the right here. And I just put, that was my flat cat. We're the wild cats here in Piedmont. And so I took flat cat with me and hid him in posts and things like that. So this is some shade cloth. So flat cat's about, roughly 6 inches, just for size reference. So these are very small plots that they used shade cloth. That black stuff is just a cloth to create artificial shade. And they had varying, this is an HS, you see a little HS on the flag, that's a high shade plot. They had low shade and then no shade plots. And then they were tracking to see, well, how do plants do in shaded areas? And the best way to explain, environmental changes with climate change is that, there's just winners and losers in an environment. And when the climate is changing, the birch shrubs become taller, providing more shade, and that's good for some plants and terrible for others. And then it's just this domino effect, since all ecosystems are based off of plants. Animals eat plants, and then other animals eat plants that eat the animals that eat plants and animals. And so you have this domino effect, this ripple effect of when the plants change in their dominance and what food is available, that has this ripple effect throughout the entire environment, since plants are the basis of food chains. So where did we go? So just a little frame of reference. We were in Alaska. I'm in Oklahoma, that little black dot there in the center, right in the middle of the state. I was in 2 locations. The star at the top is Utqiagvik, which is otherwise known as Barrow, Alaska. And then the star at the bottom, the bottom star there is Toolik Field Station. So I was in both of those locations Utqiagvik is a town of about 5,000 people right on the Arctic coast. And they have an ecology that is coastal tundra, so slightly different than the tundra that was a little further inland, in the same way that you would see different types of plants and animals in a coastal region versus a more inland region. Unfortunately, when I got to Utqiagvik, they had just had a big snow, even though it was June. So the tower that you can see in the picture on the left is typically quite a bit taller. We would be standing at the base of that tower, and it would be another good 5 or 6 feet above us. So there's probably about 5 or 6 feet of snow on the ground there. That of course we dug out to secure the towers again get them ready for the season when we arrived. Luckily though, and in a way it was kind of lucky that there was snow, because the field research area was about a mile out from our headquarters, our home base at the Bark. And so we had to carry heavy equipment out to the field sites. But with the snow, we could take dog sleds, which were pulled by a snow machine in this case, no dogs, unfortunately. That would have been so much fun. But once we unloaded the dog sled, it was too light. It would have just flopped around behind the snow machine. So somebody had to ride it back to the research station. So I volunteered with my GoPro, and you can see it's just a lot of white, white snow, white sky. It's very easy to get disoriented and lost. And I apologize if that's making you a little seasick. But that was such a wonderful experience to get to do that. Toolik is further south. And it's a field research station. So Utqiagvik is a town full of wonderful culture, and the Inupiaq people are the majority of the people that live in Utqiagvik, and they're just a lovely people. So I got to experience Alaska culture because Toolik Field Station is just a little town off of the Dalton Highway. It's 9 hours north of Fairbanks and 6 hours south of Dead Horse on the Dalton Highway. So it's extremely isolated. Those are weather ports. That's where we would live. And we had, a really nice chef that cooked food for us. Our food was just fantastic. We worked 6 days a week, but this was what our view looked like in the tundra. A lot of people always think of it being snowy, but in the summertime, 24 hours of daylight, it gets very green very fast. Here is a picture of Toolik Field Station. You can see it off in the distance. It's next to a lake called Toolik Lake. So it's just like a little miniature town, it's just a science town. That's all that lives there in various seasons. So there's another picture, a closer picture. These are bigger OTCs, open top chambers. This was in between sleet squalls that were pelting us in between, trying to set these up for the beginning of the season. So I arrived at the beginning of the season. So I did a lot of setting up of equipment and moving things. But on Sundays, we would go for hikes. That was the day off that you had where we didn't have to go out into the field and we didn't have to take measurements. And so we would hike Adigan. This is Adigan Pass. So you can see how green and beautiful it can be in the summertime. We always think of it being cold and snowy and dreary, but it is it's just such a beautiful place. That's the top of Slope Mountain, and there's a base of Slope Mountain picture there. So you can see again in the pictures just how quickly it greens up. This is about a month later, going from snow covered to this green. in just roughly 25 days, I think. And then, of course, everyone wants to know, when you're out in the field, how do you go to the bathroom? We use the towers, which are just basically permanent outhouses, but notice that it's built up because you can't dig down to build an outhouse. The towers, you would go up a flight of stairs, use the restroom, and then a truck would come and pump the tanks below. But you can't dig down due to the permafrost. It's only a few inches of soft ground, and only in the summer. And then we had showers and facilities like that that we could to use as well. But you could only shower, you got 4 minutes of shower time a week that you could use any way you wanted to. So use them wisely. So that's the end of that presentation that I have. I'm going to stop sharing and see if we have questions. Oh, that's the wrong set of tabs. Let's see. Here we go. Oh my goodness, so many questions. So first question is, as a chemistry teacher, have you ever done a class experiment involving climate change? Not a class experiment, but my first unit of the year, we looked at thermodynamics, which is a key concept in chemistry, how heat energy moves in a system. And we specifically looked at the Illicat Glacier in Greenland and how its rate of melt was affecting sea level rise. And so we just applied thermodynamics to that glacier system and explaining the glacier system and its melting rate with that. But yeah, it's a little bit tougher. I know this semester, I plan on doing ocean acidification. So we'll talk about that and use the phenomenon of oyster shells thinning as our jumping off point. So yes, I do talk about climate change, but I don't really do specific experiments, but we do learn about how chemistry plays a role in climate change. Let's see. Will areas that are currently cold, examples Canada and Russia, become warm and therefore temperate and arable? Yeah, that's really difficult to predict because, again, we're in new territory as humans. We don't really know what is going to happen to these ecosystems when the temperature continues to rise. It's difficult to predict. Canada and Russia and Alaska, these areas with permafrost are basically frozen swamps. And so when they thaw, what kind of environment, what kind of climate will they have? It's difficult to predict, but it would definitely be warmer than it is now. And it's just such a complex system. But yeah, I would assume that they would become warmer, but I don't know about becoming temperate. I would believe that their fall and springs, they would have longer seasons. Right now they have very short summers, very short, intense summers, and extremely long and brutal winters with very fast springs and falls in between. So I would assume that they would, in a way, become more temperate because those seasons would start to expand and the winters would become shorter. How long did it take you to get used to the 24 hours a day of sunlight? Did you have issues sleeping? Yeah, it didn't take too long. You had to get used to, you're used to watching the sun, move in an arc across the sky, rises in the east and it sets in the west. But when you're at the pole, it moves in a circle. And so it's noon when it's at the south and it's midnight when it's north. And it just kind of moves in a circle. So it did take a little bit of time, about a week or two, to get to where I could judge time of day based on the sunlight and the placement of the sun. Sleeping, I took a sleep mask, and then they have blackout curtains in your rooms where you slept. And so that did help quite a bit. So yeah, the sleep mask was my best friend. I don't know, I'm a good sleeper. And typically you worked so hard during the day, and hiking and going to the field and back. I mean, there was just a lot of physical labor involved in field work, which is fantastic because you definitely didn't have trouble sleeping because you would just be so tired at the end of the day. Philip would like to know, is there an average green that plants should be? Well, it depends on the species of the plant. The green index is called NDVI, which is the normalized, whatever the D stands for, I can't remember, index vegetation. And it's a small scale. I want to say it goes from 0 to 5, I think, and 5 being the greenest, 0 being the least amount of green. NDVI, I can figure that out real quick. Normalized difference vegetation. Oh gosh, even less. So it's a -1 to a +1. So -1 being not green to a +1 being as green as possible. So my measurements would have been in the decimals. I forgot about that. So yeah, ideally, I guess +1 would be the ideal most green that a plant could be. But again, it depends on the species. Some plants, if they're shade plants, they're going to be not as green because they don't need that chlorophyll. And then other plants that are more out in the sun are going to be greener than others. So, but I would think that the average, if I remember right, because it's been since 2018, the average green was running anywhere from 0.7, it's like 7 to 8 on that scale, 0.7 to 0.8. Oh, how many different types of plants did you track in the field? 8 specific plants. There were 8 focus species. So the focus species were a range of different types of plants. There were evergreen plants like, oh man, I could rattle these off until I was put on the spot. There were plants that were evergreen that stayed green year round. Think of like just miniature sized little green plants. We had some shrubs, which were the equivalent of what trees would be in the lower latitudes. Because again, plants don't grow very tall in the tundra. They stay very short. Life is hard up there. And so closer to the ground is better survival for them. They can't grow very deep root systems, which is what they would need to stabilize to grow up. So you have very short plants for the most part. And then you would have plants that were more, they would go through not evergreen, but they would have, the different, obviously phenology changes, but these were 8 key species in the tundra that they have been tracking for several decades. When you were in Alaska, how was the weather? Was it warmer than normal? Again, when I was there, the first 11 days that I was there, it snowed almost every day. And I was there from roughly the beginning of June, I'd say the June 4th to July 6th. So I was there for a little over a month. Once it got to being the more typical, what was a typical summer field season weather, it was running about mid 50s to lower 60s temperature wise. But so I was there in 2018, which was kind of a fluke year. It was colder than normal, which means I missed out on all of the mosquitoes, which I was happy to do that. They have a ton of mosquitoes in Alaska, which people don't think about. But if you think about it being like a frozen swamp, it does kind of make sense. But yeah, I missed all of the mosquitoes because it was cold a little bit longer, and they didn't come out until after I was gone. So, but it was a little, I can't compare it. But when I talked to some of the natives that lived in Utqiagvik, they did talk more about the inconsistencies in the sea ice that they depend on for whale hunts, that portions of their town being washed out into the ocean. So the people that live there would say that the climate is definitely changing. Unfortunately for humans, it doesn't take us long to adjust to our new normal. So we kind of tend to forget very quickly if there's been changes in our climate, because we just have such a short memory for that. What impacts do the changes in vegetation have on the animals in Alaska? That's an amazing question, because the animals in Alaska are very migratory. Very few will stay in one place. And so they depend on different plants being green at certain times as they're moving through their migratory patterns. And so if their migratory patterns are not aligning with when plants are at their greenest, when there's fruits available, when plants put on fruit, that can greatly impact animals like the caribou, hibernation patterns of species like bear, because they just depend on that to be green at a certain time. And so the Florida International shares their data with other researchers. And so when I was up there, there was a group there that were studying the nutrition of plants for the caribou. And they're starting to notice a change in caribou migration patterns. They are able to make those adaptations, but it does make things difficult. There's not a lot of biodiversity. There's not a lot of different types of plants and animals that can survive in such a ecosystem. And so when one plant or one animal goes through major changes, it doesn't take a whole lot to change everything else that is dependent on that fans out from that. So I think what they're starting to notice is mainly the changes in the migratory patterns and the timing of the migratory patterns of the animals. Ria's mom would like to know, have you seen any invasive species as a result of climate change in Alaska at your field site? So that was a question I actually had, when I was working with the team, and it hasn't been so much invasive species. There's been a few, but again, it's such a harsh climate. There's not a lot of plants that can come in and survive and thrive in that particular climate. But what is changing is the species dominance. And so, things like the birch, the betula, that are typically shorter shrubs, if they're getting taller, that's changing that dynamic of how plants are interacting with each other. And so it's not so much an invasive species, it's more of a shift in dominance of species that is changing how other plants are able to survive. What kinds of animals did you see other than birds? And there's so many birds in the summer, guys. Where do you think they go? Right? We always hear about birds migrating to the north in the summer, and then they come south for the winter. A lot of them go to Alaska to breed and have their broods. And so there's a ton. It's an amazing place to go for bird watching. But I got to see a lot of different types of wildlife. I saw a polar bear. I did see a polar bear. Luckily, it was 2 miles off onto the sea ice, but I did see a polar bear. All types of little rodents like voles, muskox, grizzly bear, and brown bear. Let's see, goodness, what else? Dall sheep, DAHL, Dall sheep. Mountain, they live up in the mountains. Lots of ground squirrels, Arctic ground squirrels, foxes, Arctic foxes, and red foxes. So there's quite a bit of wildlife that I did get to see while I was up there. And what kind of rocks did you see? I am not a geology person. I don't really know the names of rocks. It's the mountain ranges in that part of Alaska are right along a fault line. And so these are growing new mountains. And so a lot of granite, shale, or slate. I'm pretty sure it was shale. I don't know. It was black and it would, cleave very cleanly and flat. So, and I would assume it would be shale. Makes mountain climbing makes hiking very difficult when the rocks just like slide off the side of the mountain. But in one of the pictures, I don't know if I can share it again real fast. If I can find it, you can tell that the mountains kind of this black color, and it's because of that shale. So you can see Adigan is a good example of it. Well, oh dear, not so much, but you can see it's kind of dark gray. There's a lot of this dark black slate shale color rock. I found a piece of coal just lying on the surface. It's the craziest thing. Now I can't figure out. Stop share. There it is. So yeah, I'm not much of a rock person, but I know for sure those two things, shale, I have a piece of coal and and some granite from, you can see in the mountaintops as well.
Thank you so much, Melissa. That was really great. And thank you to our audience for joining us tonight. I hope you all had fun. I know I did. And I really enjoyed your talk again, Melissa. So thank you once again for taking the time and speaking here for us.
Yes.
And for the rest of our audience members, don't forget to mark your calendars for our next event, which will be our Ask a Geologist web series. And the topic this time will be energy storage materials. We will have Jessica Johnson. She will be speaking about renewable energies and fossil fuels and how energy is generated from these sources. So don't forget to mark your calendars for, it's going to be on February 17th and it will begin at 6 p.m. So once again, don't forget to join us for that event. And thank you once again, Melissa, and good night to everybody.
Thank you.